Good morning, everybody. Welcome to the 2020 virtual NACAT conference. I'm Kurt Ward. I'm one of your moderators this morning. Welcome to the in-cylinder pressure transducer diagnostics seminar presented by John Thornton. Before I introduce John, just a couple of housekeeping items. All of you participants this morning are in listen-only mode. You're no doubt going to have some questions this morning. Post those in the chat window. We'll be keeping track of those and we'll answer them at the end. If during the session you have a problem with your video or your audio, my best suggestion to you is to log out and log back in. We don't have any support to speak of on our end, and 9 times out of 10 it's an internet problem. You will receive credit for attending this seminar, assuming that you've logged in using the unique ID that you've been sent. If you, in fact, are watching a friend's computer and you're not logged in, you can't get credit. To get your certificate, the system will automatically generate the certificate of completion. Allow 4 to 5 days, depending on how busy the GoToWebinar system is. The more seminars, the more backed up it gets. Otherwise, you don't need to do anything else. All right, I think that's all the housekeeping. So I want to take this time to introduce John Thornton. For those of you who don't know John, he's a mobile diagnostician here in the Chicagoland area. He assists repair shop customers with engine and transmission drivability concerns, programming, diagnostics, communication issues, you name it, he's all around handy at everything. John also conducts seminars nationally for repair technicians through AutoTrain. His sessions are always awesome. They combine real-world problem solving with system operation. They focus on case studies. Boy, I don't know what else to say other than hang on. It's going to be exciting. You're going to get tons of information. And thank you, John, for being here.
You're welcome.
So with this, I'm going to click the change presenter screen. And I'm clicking on you, John. And I'm making you the presenter. And it should be changing about now. And John, you should be good to go.
You can see my screen?
I can see your screen.
Thank you, Kurt. Good morning, instructors, and welcome to your virtual conference. Again, I'm John Thornton. I'm going to lead off this virtual event with about a 90-minute discussion on in-cylinder analysis. So thank you very much for participating, and thank you, Bill, for inviting me to present. In-cylinder analysis is a much discussed topic today that one could spend hours talking about. However, we have a 90-minute window for this presentation. So because of that, I have chosen just a few topics that I'm going to focus in on as they relate to in-cylinder analysis. I have 3 goals for the class. My first goal is to explain why this method may be the best way to teach a student or a tech to help them understand the 4-stroke cycle and the 4 valve events. You know, we all know what the 4-stroke cycle is. We all understand the 4 valve events, but in-cylinder analysis allows us to actually see those events. And this lays the foundation for a better understanding of variable cam timing and variable valve lift systems. I also want to share a method for explaining, teaching this approach to engine mechanical diagnosis. And finally, I'm going to provide some examples of this method in use on a few broken vehicles. You know, in-cylinder analysis would be very simple if we didn't have valves. So this is where I'm going to start. Now, I know this sounds ridiculous, but just bear with me. So in my simple illustration here, I have a Pico pressure transducer attached to a cylinder. This is my symbol for a piston, my symbol for a rod, and a piston is stroking upward. And if I don't have valve events, I only have 2 strokes, a compression stroke and an expansion stroke. So right now I'm at bottom dead center of my compression stroke, and I would have minimum pressure in the cylinder. And As the crankshaft rotates, of course, the piston will ascend towards top dead center. And this will give me maximum pressure in the cylinder. And of course, as the crank continues to rotate, the piston will be dragged down back to bottom dead center. And we call this the expansion stroke. And this is because the volume of air above the piston is expanding and the pressure is rapidly decreasing. Now, this allows me to make the first of 2 points. I'm going to go back. The pressure that we start with is the same as the pressure that we end with. Said another way, the pressure that we end with is the same as the pressure we start with. Now, that is 100% true when there's no valve train, and it's generally true when there is actually a valve train. The other point that I'm going to start to make right now is there's a relationship between the maximum and minimum pressures in the cylinder and the stroke. Now, of course, the stroke is a function of the crank, and I use the term stroke to talk about the movement of the piston or the piston position within the cylinder. But there's a relationship, which I'll talk more about in a couple of moments. Now, the reason I started with this is I can actually duplicate this on a vehicle. You are looking at an in-cylinder pattern from a GM 5.3 liter V8 that has active fuel management. This engine is currently idling. I have a transducer in the cylinder, and I've used a scan tool to deactivate the valve train. So the piston is moving up and down, but there is no valve activity at this point in time. So as you look at the screen, you can see that whatever's occurring is pretty repeatable, and it will be repeatable for a fair amount of time. I'm going to zoom in both vertically and horizontally. My zero is right here. So that's my zero. Anything above that is positive pressure. Anything below that is negative pressure, what we call vacuum. I'm going to assign some values to these pressures. Now on my screen, every 100 millivolts of measurement is 10 PSI. So there's 300 millivolts, so that'd be 30 PSI, and you can see I'm about halfway down. So my peak pressure is 27.5 PSI. So I assume the piston's at top dead center. As the piston is being dragged down the cylinder, we lose pressure very quickly, and we start to form a vacuum. And my deepest negative pressure is a negative 13.5 PSI. So again, 100 millivolts would be 10, that's 15, so it's a little bit deeper. And as you know, a pretty good rule of thumb is 1 PSI is about 2 inches of mercury. So a negative 13.5 is about 27 inches of mercury. Now, just as a mental note, the deepest vacuum that you'll probably ever see on a gas engine, not in the manifold, but in the cylinder, is 27 to 28 inches of mercury. Normally, if you see that kind of vacuum on a gas engine, that indicates a problem, normally. Though there are some engines that might be close to that by design, but generally that would be an excessive vacuum. So this represents my piston moving up and down without valve activity. Let me zoom in on this horizontally, and I'm going to add some rotation rulers. So I'm using a picoscope, and these rulers are part of the scope's software. So for right now, I'm going to assume that my pressure here, which is the greatest, is top dead center, and it repeats 360 degrees later. Of course, the 4-stroke cycle is 720 degrees, but because I have no valve activity, I have a 360-degree event. So that's going to be top dead center, that's top dead center. I add a marker or a ruler in the middle, that's 180 degrees. So that would be top, bottom, top. Now I'm going to add some more rulers to divvy this up. So I'm going to add a total of 8. And these are in 45-degree increments. Again, this is a function of the Pico software. So 0, 45, 90, etc., all the way to 360 degrees. Now I'm doing this for a reason, and I'm preparing to ask you a question. But before I do, I'm going to pop up a green horizontal broken line, and that's my 0 line. This is just for visual conversation. So here's my question. As you look from 0 to 360 degrees, would you say that the cylinder is under pressure above 0 the majority of that time, or would you say that the cylinder is under vacuum the majority of that time? Well, of course, as you know, the cylinder is under negative pressure, or the cylinder is under vacuum. And I ask this, and I note this so I can make a pretty important point. This is bottom dead center. Now, if you think of the conventional compression stroke, the way that most of us learned the compression stroke, it started at bottom dead center and it ended at top dead center. And that's always been a fairly convenient way to discuss it. But take a close look here. I'm going to start at bottom dead center. Now I'm going to call that 0, even though it's 180 for my reference, but that's just my starting point. So 0, 45, 90, 135. That crank has rotated 135 degrees out of a possible 180, and we're still in a vacuum. Said another way, we start to build pressure right here. So that's atmospheric pressure right there, and then that's peak pressure. So we have less than 45 degrees of crank rotation to build pressure in that cylinder. Now, granted, there's no valve action here, but even in a regular running cylinder with good compression, you don't have a lot of time, not much more than 45 degrees. So this is why very small leaks in a cylinder can cause low RPM misfires. You know, certainly if a chunk of an exhaust valve is missing, that's a problem. But you can have valve face seats that don't match well. Maybe there's excessive clearance in the guide, or there's just some kind of wear issue on the valve itself that can cause low RPM misfires. So a takeaway is that we don't have a lot of time to build pressure in a cylinder. So a lot of things have to be right. This is the same cylinder with the valve train reactivated. So this is what we're going to talk about here in just a moment or two. But before I transition into a normal running compression pattern from what I showed you here, I want to leave you with 3 points. The pressure we start with is the pressure we end with. And this is true in a normal running compression pattern. It's a function of when the valves open and close, but you'll see me reference that and talk about that through the presentation. Another point, which I started to make, and I'm going to go back, there is a very strong relationship between maximum and minimum pressures in a cylinder and stroke. So in this good running example, we hit 70 PSI of peak pressure and we pulled down to about 20 inches of vacuum. In my example, without valve activity, I only hit 27, but I pulled much deeper. And what I like you to think about is whatever pressure you start with, as the piston is being dragged down the cylinder, we have to relieve the pressure. The lower the pressure that you start with, you relieve it sooner. So if I relieve it here, I've got more stroke, the downward movement of the piston, to create a low pressure area in the cylinder. If I start with higher pressures, more of the stroke is used to relieve the pressure. And by the time I get down to atmospheric, there's not a lot of stroke left, a lot of piston movement left to create a vacuum. So this is why, generally speaking, the higher the pressure in the cylinder, the lower that expansion vacuum will be. Or the lower the pressure, the deeper that expansion vacuum will be. So there's a relationship there, and I'll talk more about that. And finally, my point is there's not a lot of time in crankshaft degrees to build pressure on that compression stroke, which is why everything has to be correct. So having said that, we're going to now move into what I would call a conventional, typical in-cylinder running compression pattern. I am not going to do cranking compression for a couple of reasons. One, because of my time, and secondly, when you crank an engine over, as you know, there's very little vacuum in the manifold and in the cylinder. So the intake events are not well defined with the loss of vacuum. So I'm going to use running compression because it's easier to see the valve events, it's easier to see the vacuum in the pattern. So generally, when we start this analysis, we fill the screen with the 4-stroke cycle, 720 degrees, and we usually start at top dead center. So you can see my flashing yellow circles. This is my top dead center, top dead center. Now, I've always used a couple words as an adjective to describe this. And I've always called this a reasonably accurate top dead center. We are not using a dial indicator and a degree wheel to find TDC. We're using a pressure transducer and pressure buildup in a cylinder to identify where we think it's going to be. Now, please don't get me wrong. This is a reasonably good method. It's reliable. A lot of diagnostics can be done based upon this, but it's important to note it's reasonably accurate. And I will tell you that if you were to compare this pattern to a crank sensor signal, and as you elevated the RPM up and down, that point would move a little bit. Not a lot, but it's measurable. So it's a reasonably accurate top dead center. So our analysis starts with that. However, there can be problems in an engine in which the greatest pressure is not top dead center. And I want to show you how to do that. And then I'm going to give you an example of that. So first of all, so this is the same pattern. I've added my green broken line, it is 0. And I've added some rotation rulers. So I want you to notice something. That's my 0. So from here, we are building pressure to a peak. Here, we are losing pressure at the same point. That area here is called a compression tower. Bernie Thompson from Automotive Test Solutions, I think, coined that term. I always like credit for that. That's called the compression tower. And what I want to add to it is that this compression tower has symmetry. And what I mean by symmetry is this. The way we build pressure is similar to the way that we lose pressure. If you look where my black arrows are, either on the left side or the right side, if you were to measure time or crank degrees between that spot right there and that spot, you would find it would be very close or equal to here to here. Now, I've put up a ruler and a 0 line to help your eyes focus. But with a little bit of practice, you can usually look at a tower and determine if it's symmetrical. So if a tower is symmetrical, it's pretty fair to say that's a reasonably accurate top dead center. Let me show you an example of one that's not. This is a pattern from a Mazda with a 2.3 turbo gasoline direct injected engine that has a burnt exhaust valve. It has a significant leak in the cylinder, and I am performing a cranking compression test. I'm going to open this up and define some points. So my peak pressure cranking, and this is horrible, of course, is 27 psi. The expansion stroke vacuum pulled very deep at 13.4 inches. And this goes back to what I said earlier. There's a relationship between the pressures and the stroke. If I start with low pressure and the piston is dragged all the way down, I have plenty of time to build vacuum in the cylinder. So that's unusually low. You can probably tell already by looking at this screen that the compression tower is not symmetrical. Let me just enhance that a little bit. So I've put up overlays, and I can tell you for a fact that is not top dead center. It's not close to top dead center, but nonetheless, I put the overlay there just to make my measurement. And I think you'd agree with me that the distance from that point where we just start to build pressure in here is much greater than that distance. So we do not have symmetry in a compression tower. And if you don't have symmetry in a compression tower, you do not have a reasonably accurate top dead center. So do not continue further with trying to determine valve activity. So clearly in this case, one does not have to go much further to say we have a significant problem in the cylinder, but I use this to make a point. So having said that, let's get back on track. So I have my Ford 4.6 liter here, running compression, known good cylinder. I've identified my reasonably accurate TDCs, and I'm going to use a built-in feature of the picoscope and bring on these overlays or these rulers. Picoscope and Bernie Thompson automotive test solution scopes have the ability to kind of automate this process. If you're using a snap-on scope as an example, they do not have built-in overlays, unfortunately. So there are a few ways to do that, but one way from an instructional viewpoint would be to save the screen and bring it into a PowerPoint and create your own rulers within a PowerPoint. Something that I did many, many years ago before Pico added this feature. So I have broken this up into 4 180-degree events. So that's my 0, 180, 360, 540, and then back to 720. So those are my 4 equal events. And I do this so I can define my 4 strokes. Now, this is not to insult your intelligence. Of course, you know the strokes. This is just to make an observation. So my first stroke, as we travel from left to right on the screen, is the expansion stroke. And this just allows me to make a point. When we are in cylinder with a transducer, we are not measuring combustion pressures, we are measuring compression pressures, the ability of the cylinder to bring air in and move air out. So we don't have a power stroke, we have an expansion stroke. The expansion stroke starts at top dead center, reasonably accurate, and it ends at 180 degrees bottom dead center. So I say this because this is non-negotiable. As long as I have symmetrical compression towers, and I have a reasonably accurate TDC, and my cursors are accurate, that's 180 degrees of stroke. The next stroke, of course, will be exhaust. It starts at bottom dead center, theoretically, and it ends at top dead center. Again, non-negotiable, it's 360 degrees, that's top dead center. Now, of course, I'm not taking into account what the valves are doing, but that's the position of the piston and the rod. The next stroke, of course, will be intake. Top dead center to bottom dead center. And finally, the compression stroke. So again, I do this because once I have a reasonably accurate TDC with symmetrical compression towers, I can put up these markers, these rulers, these overlays, and I am preparing for the next step to identify events within the pattern. So now I'm going to kind of repeat what I just said, but I'm going to add detail to these 4 strokes. So we're going to start with the expansion stroke. And while there's many items to be discussed, could be discussed in each of these strokes, I am going to focus on what I consider to be the most important for the time that we have. So we start at top dead center, and then the piston is being dragged down the cylinder to bottom dead center, where the 180 marker is. And we notice that right here, where my black arrow is, we have an abrupt change in pressure, or a delta pressure. So there's a change in pressure. Now, I suspect all of you know what happened here. I don't want to memorize anything. I want to start to form an understanding of what I'm looking at on these types of patterns. So anytime that I see a change in pressure, there are 3 things that come to mind. There's a couple other things I can add, but there's 3 things that come to mind. And I have these, in the handout as well, but I'll just show you them here, then I'm going to go back. The first thing that can cause a change in pressure is that a piston changes direction. Well, you see that here. Piston changed direction. There's a change in pressure. The other reasons for a change in pressure can be that a valve opened or that a valve closed. Additionally, changes in pressure, which I don't have highlighted in the notes, can be due to airflow dynamics. And I'm going to give you an example of what I mean by this. when I teach this class, many times I'll ask the question to the group, where is your pressure transducer? And I see the look on the faces of those in attendance, which might be the same look that's on your face right now, wondering what does John mean by that? Because clearly the pressure transducer is connected to the cylinder, and 100%, we are connected to the cylinder via the spark plug. However, that is only true when the valves are closed. So right now, as the piston comes up on compression, the valves are closed and the transducer sees what's inside the cylinder. But once we go from compression to expansion, the piston, of course, starts to move down. And generally speaking, in the last third of the expansion stroke crank rotation, the last 60 degrees, that exhaust valve is going to open. So in my illustration, you can see the exhaust valve is going to open. So now, when I ask the question, where is my pressure transducer? Well, of course, the answer is yeah, I'm in the cylinder, but where else are we? And of course, you are correct, we're in the exhaust manifold. So we are in the cylinder and we are in the exhaust manifold. I'll tell you why this is important. Imagine you're working on a running engine, a 4-cylinder, and you're in one of the 4 cylinders, so the other 3 are still exhausting, or you're in half of a V8. The exhaust pressure pulses from those other cylinders are now seen in the cylinder that we are analyzing. That's an example of airflow dynamics. Now that occurred because the exhaust valve is open in this case. So that's something to keep in mind as we move through this discussion and in general when you perform this type of analysis. So as I'm sure you know, this change in pressure is due to the exhaust valve opening, EVO. So once again, we were at top dead center. The piston was dragged down. There was a change in pressure before bottom dead center, and that's because this is where the exhaust valve opens. So my rule of thumb for specs is most EVOs are 60 to 30 degrees before bottom dead center. Now, I have to always be careful with these kinds of numbers. There are some engines that are 55 to 60. There are some engines that are 35 to 40. So this is a window. This is a window. You can be within this window and still have jumped a tooth or two on a sprocket. But this is a reasonable window. Usually, if you're out of this window, that would probably indicate a problem. But once again, in our business, there are exceptions. And sometimes you deal with like high performance engines that breathe well, maybe like a Hemi, and it might be outside of the 60 degrees. But most engines are probably going to be within that window. So that's my number, 60 to 30 degrees before bottom dead center. And again, the reason for the change in pressure is because that exhaust valve opened. I'm going to add one more piece. You'll see my green broken horizontal line will pop again. You heard me say almost at the beginning of our conversation that the pressure we start with is the pressure that we end with. And I've got plenty more to say about that, but please notice that the depth of vacuum reached on the expansion stroke is the same as the depth of vacuum reached on the intake stroke. And this is not coincidental. There's a very sound reason for that. This is where the pressure starts, and this is where it ends. And again, there's symmetry in the valve train as well, and I'll talk more about that. So as you do your analysis, as you study this, as you talk about this with your students, if you decide to do that, you always want to kind of compare that point to that point. The vast majority of gas engines, they will be very, very close. There will be some engines that there may be a 1 or 2 inch difference, a 1 or 2 inch mercury difference between them, but most engines will be pretty close. When you have significant problems with cam timing, there will be a difference. For example, if I have a double overhead cam engine and the exhaust cam is retarded, which means everything occurs late, the exhaust valve will open later. So instead of opening here as an example, it would open over here, and there would be more vacuum pulled until that valve opened. So not only does the exhaust valve open late, it closes later, which means it closes into overlap, which gives the intake low vacuum. So if I have a retarded exhaust cam, one of many clues is that this would be deeper and this would be shallower or less deep. So I don't want to memorize that. I just use that as an example, but I want to understand why there's a relationship. And I've got more to say about that when I kind of wrap up this section. So let's move to the exhaust stroke. Once upon a time, the exhaust stroke in this analysis was considered to be the easiest stroke to understand. No, we have opened the exhaust valve 60 to 30 degrees before bottom dead center. So the valve is opening, and by the time the piston has moved upward to clear out the byproducts, and in this case it's just removing air, but as it's moving upward, the valve is opening and there should be no obstruction. There should be no, what I call, exhaust path restriction. So the main point here is I expect my exhaust stroke to be pretty much close to 0 PSI or a little bit less, but I expect it to be close to 0 PSI. I don't really want to see it much more than 0 PSI. Now keep in mind, my transducer, which is attached to my cylinder, is now also seeing the impact of the other cylinder's exhaust, the little airflow dynamics here. So in some cases, you may have many oscillations, and in some cases, it'll be a little flatter. So for years, this is kind of what we saw. But of course, as technology moves forward, we see exceptions. So I'm going to show you an exception using two examples. This is a known good in cylinder of a GM 4200 that I took many years ago. And a 4200 was first introduced in 2002, and it was a new engine, and one of its features, it was the first engine to have cam phasing on the exhaust cam. So keep that in mind, and you'll notice where my black arrow is that I have an EVO, I have 0 PSI for the vast majority of the exhaust stroke, and at the very end, there's a little bump in positive pressure. I wonder if that's good or if that's bad. I move forward a few years. This is a GM 1.4 liter turbo Ecotec, maybe you find in a cruise, that has normal idle cam phase. And I'll define that in a second as well, but you'll notice I have an EVO. There's a little bit of noise in this pattern, but it's okay. I have an EVO, I have a pretty good 0, and then right here you can see towards the end of the exhaust stroke, beginning of the intake, there's a positive going pressure pulse. And I wonder if that's good or bad. So I need to talk about this, and I've used this example so I can make an additional point. Generally speaking, when you phase an exhaust cam, you retard the cam from its default position. So said another way, if an exhaust cam is capable of being phased, but it's not, the exhaust cam is installed fully advanced. And then when it's phased, running down the road, sometimes in the bay or motivated by a scan tool, it will then retard. So I'm going to go back to the 4200 for a moment. If the exhaust cam by default is fully advanced, and it is, both valve events, when the exhaust valve opens and when the exhaust valve closes, occur sooner or earlier. I just want to focus right now on when the exhaust valve closes. So if you think about it logically, and I realize with my webcam, you probably can't see my hands as well as I would like, but imagine my piston is moving up on that exhaust stroke and it's approaching top dead center. And normally the exhaust valve would still be open and there's no back pressure in the cylinder. But if that valve closes too soon, there will be some trapped pressure and we'll see a positive going pressure pulse. So the bottom line on that 4200, that's perfectly normal. That's normal. Now, if that engine did not have cam phasing, I probably wouldn't say that. It brings me back to this 1.4. This is something that each technician, instructor decides on their own on how they're going to handle this. On this engine, the PCM phases the cams at idle. So these cams are currently phasing. And right now at idle, this exhaust cam is advancing. So it's being commanded to advance. If I disconnect the two magnetic actuators mounted in front of the engine, I see this. So you can see my note, no cam phase. Well, a couple things happened. One, the peak shifted to the left, it advanced, and the pulse got higher. It's almost 16 PSI. So again, I'm trying to make 2 points. I'm trying not to be, I don't want to be confusing. That's not my goal. So this is normal. So most of us today, we save patterns. So when I did this 1.4 liter, my thought was that in the future, I will diagnose a 1.4 turbo Ecotec in which there's a cam timing problem. I would like to have known good in my database. So I have a choice. I can save known good with the cams phasing, or I can save known good with the cams not phasing. Of course, I did both, but in general, when I am doing documentation and I'm saving, I will disconnect the solenoids, I will disconnect the actuators, I will prevent the cam from phasing, and I will note it in my notes on my scope patterns. That is clearly up to you. So getting back to my key point here. An exhaust valve that closes too soon, I'll talk more about examples of that, but an exhaust valve that closes too soon will have a pressure pulse, a pressure increase towards the end of an exhaust stroke. So good or bad, that's going to occur. Now, if I have cam phasing, and of course, we would know what's in front of us, but if I have cam phasing on the exhaust cam, that's probably going to be normal. But if I don't have cam phasing and I see that pressure pulse, that's probably not going to be normal. So if I were to summarize very quickly, typically, this is what an exhaust stroke looks like, close to 0 PSI across the 180 degrees. If we have phasing involved, we tend to see a pressure pulse.
Good morning.
Morning.
How we doing?
Hey, Bill. Okay, I think we're, Kurt, is everything okay right now?
Okay, not great, not fantastic, just okay.
Yeah, it sounds like Bill failed
What's
to
going
mute
on?
himself.
I'll get a hold of Bill.
Okay, I'm going to continue. I apologize. We had a little background here.
Yeah, so, go ahead and we'll get Bill to mute himself.
Okay.
Thanks, John.
So no problem. So now we move to the intake stroke.
Really got to do a lot.
Of the 4 strokes that we have to talk
Did you
about.
get that SOP stuff SOP stuff I sent the other day?
The intake stroke is the most challenging stroke to understand. So what I'm going to do, I'm going to take this section right here of the intake stroke, and I'm going to blow it up. And I'm going to identify, 3 key spots that I want to talk about. So there's a spot here, and a spot here. Now this is at the beginning of the compression stroke, but it's a continuation of intake. So this is the first spot. This is right here. You will notice that I will not provide any kind of spec or guideline for when an exhaust valve is supposed to close or when an intake valve is supposed to open.
Yeah.
Because in my mind, this is a very difficult thing to do. And let me explain why. You'll see here, I say there's 3 events occurring. And the 3 events that are occurring are this. The piston is changing direction. So we're going from piston approaching top dead center, now being dragged down as we start the intake stroke. And anytime a piston changes direction, there's going to be a pressure change. We have an exhaust valve that is closing, and we have an intake valve that's opening. So I have 3 events that are occurring at about the same time. Additionally, my transducer, which is in the cylinder, is seeing the effects of the exhaust manifold. And then as we get into overlap, and not all engines have overlap these days, but most still have overlap, now we have airflow dynamics. Now we have what's in the cylinder, what's in the exhaust, and what's in the intake. And if the pressure here is low enough, we might have some type of movement like this, reversion. Now, if the engine is designed well enough, there may be scavenging and it may go in the other direction. But I don't know that for sure. But the bottom line is there's so much activity going on right here, it can be very difficult to easily identify when that intake valve opened and when that exhaust valve closed. It's very difficult to do. Now, when cars are broke and there's significant failures, it's easier to actually identify some of those locations. But on most engines, that's a challenge. That's a challenge. So I have another spot right here. I call this is the point at which the deepest vacuum on the intake stroke is first reached. So this is not a textbook definition. This is not exactly when the intake valve opened or when the exhaust valve closed, but it's an indication of both. That point will shift left or right as a function of intake valve opening and exhaust valve closing. Let me give you an example of what I mean. So my baseline number, this is an opinion. My baseline number is I expect the point at which my deepest vacuum is first reached to be approximately 30 to 60 degrees after top dead center. Now, some of you who may have been doing this for a long time and you may not agree with that number, and that's okay. That's fine. But what I would ask is if you're not doing this, that you look at this. You look at this point in your analysis and you just start making a measurement. You know, where did that point occur on this engine that I'm working on? And after you've done 10, 100, whatever, you'll have a feel for the numbers. So that's where my numbers come from. It's kind of a feel. But again, I think I can use that point as an indication, confirmation that there's a problem with cam timing. So let me show you a specific Toyota example. I have a Toyota Camry with a 2.4 liter engine that has intake cam phasing only. And I'm going to use the scan tool to phase the intake cam. But a little bit of background first. In general, when you phase an intake cam, you advance it, kind of the opposite of an exhaust cam. So when an intake cam is not being phased, it's fully retarded. That's its default position. And then when you phase it, it advances. So this engine has a 50-degree phase angle. So it's pretty significant. So I'm going to show you in a moment full phase for this particular RPM. And there's a couple things that are going to change, but initially, here's what I'd like you to do, please. Look right about here, this area right here. So right now, the intake cam is fully retarded by design, and I'm going to advance it, which means things are going to move to your left. So watch what happens as I advance this, please. So that's fully retarded. That's fully advanced. Fully retarded, fully advanced. Yes, other things moved, no doubt. But you can see the point at which my deepest vacuum first occurred has moved to the left. It has moved to the left. So it's an indicator. It's an indicator. Now there's something else you may have noticed, and this is going to lead into our next point here. Right now at idle with the intake cam fully retarded, my peak compression, rough math, is about 46 PSI. Reasonable for this engine. When I advance the cam, the scales on the screen don't change, so I'm not pulling any fast ones. Scales stay the same. My pressure rises dramatically. Here, it's about 76 PSI. Here, it's a little bit higher. I'm transitioning, but you can see the pressure went from 76. It went to 76 from about 46. So a significant pressure increase. Why? There's two primary reasons why pressure will change like this inside of a cylinder. And they are, in no particular order, the amount of pressure that's in the cylinder and or the intake manifold, and when the intake valve closes. And in this case, it's more about when the intake valve closes. I'm going to move back a little bit from my camera, so hopefully you can get a better sense of my hand here. But imagine for a moment, my fist is a piston and I'm stroking a cylinder. I'm going from bottom to top. Now, we don't actually build pressure in the cylinder until you close the intake valve. So if you close the intake valve late, I close the intake valve here, that's where I start to build pressure. So there's less air mass to compress. But if I close the intake valve sooner or earlier, there's more air mass to compress. So generally speaking, all things being equal, anytime you advance an intake cam, you expect to see an increase in peak pressures. That's why we saw it here. The other reason would be a change in pressure in the manifold, going from 20 inches of vacuum to 0 inches of vacuum. I'll talk more about that when I come to an appropriate example, but those are the two variables that we see in diagnostics that will affect that pressure point. So finally, as we move to the compression stroke, so I talked about the complexity of what's happening here. This is a good reference, 30 to 60 degrees after top dead center, and now we come to intake valve closing. And of the 4 valve events, this is one of the most critical for being able to build pressure once again in the cylinder. So my rule of thumb is I expect most IVCs, intake valve closings, to occur 40 to 60 degrees after bottom dead center. So that is my expectation. So here's my bottom dead center, and that point's about 40 to 60 degrees after bottom dead center. So I've really given you 2 specs on valve timing: exhaust valve opening, which I'll show in a second, and intake valve closing. And I added an opinion that this point here, typically 30 to 60 degrees after top dead center. Now, I'm going to wrap this up before we move into some vehicles with issues. I'm going to pop up my green horizontal line again. And I'm going to make a comment you heard me say at the very beginning, which I think is important to keep in mind. The pressure that you start with is the pressure you end with. And there's a reason for that. So these are my guidelines. So let's just say for discussion purposes, my intake valve closing is 60 degrees after bottom dead center, and my EVO is 60 degrees before bottom dead center. Rarely ever will they be the same, but for conversation, we're going to go ahead and take that liberty. So I'm going to start here, bottom dead center. The piston moves up, 60 degrees later, the intake valve closes. So we have 120 crank degrees to start and build pressure. Now, a lot of that, of course, is to get out of our vacuum stroke, but nonetheless, we have 120 degrees to build pressure, and we build some pressure. Then, if that exhaust valve closes 60 degrees before bottom dead center, we have 120 degrees to lose pressure, which gives us our symmetrical compression tower. So I had 120 degrees to build, and I had 120 degrees to lose. That's why the towers look the way they do. And now you can imagine if the point at which that intake valve closes shifts dramatically left or right, or the point at which the exhaust valve opens shifts dramatically left or right, it will impact our symmetrical compression towers. So again, not all cam timing specs are going to fit neatly in my windows. Many are, but I could have a 60-degree EVO here and a 45-degree IVC here. So it's not perfect, but they're close. They're close. So this is an important concept. The pressure you start with should be close to the pressure you end with. And that's why, again, you heard me say, the depth of the vacuum achieved here should be very similar to the depth of vacuum achieved here. And of course, there's much more that can be said about this, but I think this provides hopefully a foundation for understanding how the valve events affect this pattern and where to expect these events. So we're about halfway through, and I want to use the kind of the remainder of my time to talk about some mechanical issues. So I've chosen 3 to talk about: exhaust path restrictions, intake path restrictions, and cam timing issues. Now, exhaust path restrictions and cam timing issues are very common. I see these on a regular basis. Intake path restrictions, a little less common, but I've chosen it for a reason that I'll explain when I get there. So I'm going to start out with an exhaust path restriction. And as the name suggests, an exhaust path restriction prevents us from maintaining that 0 PSI across the exhaust stroke. So an exhaust path restriction can show up as a rise in pressure just after exhaust valve opening. So the piston is rising, instead of hitting 0, it goes to 2, 4, 6, 8. Or, as we saw, an exhaust path restriction can show up as a slight pressure pulse towards the end of the exhaust stroke. You know, maybe the last third, the last quarter of the exhaust stroke. These are examples of exhaust path restrictions. Worst case scenario, exhaust valve doesn't open. Could have a restricted converter. Now the next few I group together. While they're not necessarily the same thing, I group them together. And here's what I'm getting at. We've kind of discussed this, so this is nothing new here. If a cam, whether it's one cam or double overhead cam, exhaust cam, if the cam timing is advanced, everything occurs earlier. Valves open earlier, valves close earlier. So you'll notice I've highlighted in blue, closes earlier, because that's what I'm interested in right now. So if the piston is coming up on that exhaust stroke and that exhaust valve closes too soon, we trap air and we have the pressure pulse. The same thing happens with a worn lobe. And let me make sure we're clear on this. So I just have a cam lobe illustration, base circle with the lobe. That's my center. So our rotation as we look at that is clockwise. So in black, this is when the valve would start to open. I'm not worrying about clearances in the valve train. So this is when the valve would start to open. We would have peak lift, and then we would control the close. Blue represents wear and tear. So blue is my worn lobe. And lobes don't wear this evenly, of course, but to make my point and to help you understand. So if the lobe is worn, the valve will open later. It will open later. That's what they do. They open later. There will probably be less lift and there'll probably be less duration. But to our point, not only does it open later, it closes early. And this is important. I want to make sure you take a close look at this and you understand why a worn lobe causes a valve to close early. So it's going to close earlier. So that's why an advanced cam and a worn lobe on the end of the exhaust stroke act the same way. In both cases, they cause that valve to close too soon, and they will be a possible reason for a pressure pulse. And a misadjusted valve, the one that's loose, is a little bit like worn lobe. Without the wear, it's just the clearance. So it has a similar impact. So let's take a look at a vehicle. I'm going to give you a little bit of background, then I'm going to do the analysis. So I have an 06 F-150 5.4 3-valve, and bank 1 cylinders do not contribute. I am fortunate I have a Ford scan tool, the IDS, and I'm going to perform what they call a relative compression test. And if you haven't done this before, this is a scan tool driven test that works in conjunction with the PCM that asks the tech to depress the accelerator pedal to the floor and crank the engine over for about 10 seconds. And then the PCM uses the crankshaft sensor signal to determine if we have relatively even compression pulses as they impact the RPM. And as I look at this, my results, all cylinders are pretty much the same. There's a couple here that are a little bit low, but they're reasonable. So this suggests that all 8 cylinders have about the same compression. So that's the first observation from the scan tool. The compression, it looks pretty good in the cylinders. Remember, this is compression, not combustion. I look at the power balance or the real-time misfire screen, and the blue line is current and the gray is historical. So I've had this engine running for a little bit, but you can see the trend is at cylinder number 1, 3, 2, and 4 are dropping RPM. Those are our misfiring cylinders. If I tighten this up by elevating the RPM, you can still see it's 1, 3, 2, 4 bank 1 cylinders. So bank 1 cylinders are misfiring at idle and off idle, but they have good compression. So there's usually two things that a tech will probably think about. One would be possibly cam timing or maybe a restriction in the exhaust. These are good possibilities. So fortunately on this engine, they have good cam timing PIDs that do not turn off if there is an issue. They'll do not default to 0. So right now at idle, when this engine is misfiring, both my cams, bank 1 and bank 2, are close to 0 degrees where they're supposed to be. So the cam timing looks pretty good. And finally, I'm going to look at some fuel trims. I do this because, quite frankly, I can't help myself. It's so important in the analysis. But anytime there's an imbalance in airflow bank to bank on an MAF engine, you can usually see opposing or skewed fuel trims. So right now at idle, my bank 1 trims, if I add them together, about a negative 10%. My bank 2 trims, and there's nothing wrong with bank 2, you can see they're just over 20%. If I increase the RPM, and I let the trim stabilize, bank 2 goes extremely negative, about 35%. Bank 1 goes extremely positive, about 45%. I'm not going to worry about the trims. These are clues that suggest there may be an imbalance in airflow bank to bank. Well, if it's not cam timing, restriction of the exhaust is probably a next good item to consider. Now, there's all sorts of ways to check for restrictions in the exhaust. A conventional way has been to pull an O2 or drop the exhaust. I'm not going to necessarily argue against that, but at the end of the day, the restriction in the exhaust causes a problem for the cylinder. So I'm going to go in the cylinder, and again, I realize this can be a tough engine to pull plugs on, but if I can pull the plugs, I'm going to go in the cylinder. So I'm looking at cylinder number 1, running compression. And at first glance, things don't look too bad. Let me zoom in a little bit and identify my 0 line. So there's my 0. And I think you'll agree with me. We had an EVO, the pressure rose above 0, not much, but above 0. And there's some oscillations because there's 3 other cylinders. We have some airflow dynamics on that exhaust stroke. If I make a measurement, my scaling, 40 millivolts is about 40 PSI. So I have about 4 PSI of in-cylinder back pressure, and this is where it counts. This is where it counts. This is why I'm in the cylinder. Now, if I vertically zoom, so again, the 40 millivolts is 4 PSI. So at times it's above, at times it's below, but it's not 0. So generally, when you have a converter, as an example, that has a restriction, once the valve opens and the pressure rises back, it will go higher than 0. So this would be a clue of a converter as opposed to an advanced exhaust cam or a worn lobe. Now keep in mind, a converter can be restricted in such a way that it requires a lot of air mass. So if an engine's idling pulling 4, 5, 6 grams of air, and the converter does not restrict that, I'm not going to see anything. So I may have to elevate the RPM. So just to kind of make that point, on this same engine, I'm going to do a brake torque in reverse. Now on this Ford engine, when I do a brake torque in reverse, and I always do them aggressively, I put the accelerator pedal to the floor, because there's no vehicle speed, the PCM is not going to let me do what I want. So the PCM is going to open the throttle blade further, but it's not going to open it all the way. That's what I mean by limited throttle. Take a close look at my pattern and look at my 0. You see it? That 0.5 is 50 PSI. So those exhausts, this whole pattern has been elevated upward. So that's, and you can see my pressure, that's 250 PSI. So I'm moving some air in this cylinder, but that's about 40 some PSI of back pressure. And I tell you that just because, again, in some cases, especially if the restriction is further downstream in exhaust, you may have to create a lot of air mass to see the impact on your analysis. Now, what I'm going to do is I'm going to do a kind of what I call a live diagnosis. Now, I don't have a vehicle in front of me, but I have some Pico screens, some Pico screens saved from this particular Hemi. So this is not in the handout, but I want to give you an idea of how some of these measurements are being done. So I'm going to try to accomplish a few goals with this example. So we have a 2010 Challenger 5.7 Hemi with a single cylinder misfire. And please take my word on this, the diagnosis has been done that we're kind of to the point that we suspect it's mechanical. So I'm going to open up a Pico file that I have running in the background. And I realize due to bandwidth, it may take a moment in time for everybody to see this on their screen. Kurt, if you're listening to me, can you see this on your screen?
Yeah, John, I can see it just fine.
Okay, so I guess we should all be there. So this is a known good cylinder. Thank you for that, Kurt. So this is a known good cylinder running compression from startup. So I'm going to use this as my baseline before I show you the cylinder that's got a problem. So there's my zero line right there. And that's what that 1 volt is 100 PSI, just as reference. So I'm going to do some manipulation. So I'm going to zoom in horizontally first. Again, if you have a different scope, you would have different controls. And I'm going to zoom in vertically as well, just to kind of make it taller and take full advantage of my screen. I'm going to lift my pattern up so my zero is a little bit higher. And I'm going to grab my cursor here and put it at my zero. Again, we're talking about exhaust pass restriction, so I'm not pulling any fast ones. That's our focus. I'm going to zoom in some more horizontally. And as you can see, if I walk through this pattern, our exhaust stroke is pretty close to zero. And that would be normal. Now, what I want to do is I'm going to make a couple of measurements with this known good one as an example that we will reference when we look at the bad one. So I'm going to remove this here temporarily. I'm going to zoom in some more. So up at top here is my horizontal zoom on Pico. So normally, if I click the arrow, it will do this incrementally. Now I want a little bit more. So if I hit the arrow, it's going to be too much. So I can, on Pico, I can highlight the box. I'm going to type in 60, a zoom factor of 60. So you can't see my fingers, but you can see the number change. I'm going to hit enter, and this opens it up. So I could do 66, but 60 is pretty good. So I'm going to show you how I pull out my rotation rulers. So in the lower right-hand corner, I'm going to grab my ruler. It says 0 degrees, and my towers look somewhat symmetrical, so I have a reasonably accurate TDC. I've already got this set up quickly so I can move along here. So that's 720 degrees. And these are my 4 180-degree increments, my 4 strokes. And I want to make 2 measurements. The first measurement I want to make is exhaust valve opening. So my cursors are over here. So I want Pico to do most of the work for me. So I'm going to put this on bottom dead center. Now I'm pretty good with a mouse, so I got it pretty darn close, 179 point, oh, that's where it was, but it's not too far away. But with Pico, if I highlight that box and type in 180, the cursor will move automatically. So 180, watch the cursor when I press enter, and it moves right there. Then I grab my other cursor, and I'm looking for my EVO. And the difference between the 180 and where I am is at 57.79. That's my EVO. Now, I want to show you a method that I use. A lot of times when you do this, you can definitely see there's a change in pressure right here, but it's almost always kind of a very short, almost horizontal line. So I would like to enhance that. I want to do this as best as I can. So my method is once I put on my rulers, my overlay, I will zoom in vertically, and it's always, it's a function of practice, personal preference. So I'm going to make this times 10. Now I'm going to make it one more times 20. And I'm going to pull this up. And obviously I'm clipping the top of the pattern, but I no longer care. It's a little bit fuzzy, so I'm going to turn a filter on. It's going to activate a filter, and I don't want to over filter, so I'm going to run about 6 kilohertz. And this is practice makes perfect type of thing. And now when I put this in here, I'm going to try to get to the best that I can. Now, I didn't really change much, but I wanted you to see the method. So it's 58 degrees. So if you could make a mental note, my EVO on this good cylinder is about 58 degrees before bottom and center, within our window of 60 to 30. So I'm okay with that. Now I'm going to do one other thing. I'm going to try to measure the duration of this event. Now, this is a difficult thing to do because again, that's a very busy area here with piston changing direction. I know the exhaust valve is closing someplace around here. The intake valve is opening. There's some airflow dynamics, as you can see, but I'm going to take a swag at it. So I'm going to leave this cursor right here. I'm going to move this one, and I'm going to say, and I may not be right, that peak right there is maybe when the exhaust valve closed. Maybe not, but my duration from here to here is 230 degrees. So there's two notes I like you to make. When the EVO was about 58, duration about 230. Now I'm going to open up the cylinder that's got the problem. And I'm just going to wait a moment to make sure that, again, bandwidth, that everybody sees this on their screen. Kurt, we okay?
You are good.
All right, so we will. So this is it's a similar scope screen setup, but this is the bad cylinder. So I will try to duplicate everything I did before. So I'm going to start to zoom in horizontally first. Then I'm going to zoom in vertically. Then I'm going to lift the pattern up a little bit. And I'm going to bring my cursor down to my 0 line because we're dealing with exhaust path restrictions, this discussion. And you can see right away, there's something weird with the exhaust stroke. So I'm going to zoom in some more. And if I walk through the pattern from when the engine was first cranked and started, and then the pressure stabilized, whatever's going on, it's consistent. So I'm going to zoom in some more horizontally. And you can see we have an EVO. We hit 0 PSI. We stayed there for a while, which probably suggests that we don't have a restricted catalytic converter. And of course, if it's a single cylinder event, it probably wouldn't be a catalytic converter anyway. And then we have a pressure pulse and this pressure pulse is hitting about 25 PSI. So it's a pretty significant pressure pulse. So I would like to analyze this a little bit and try to determine what's wrong. So once again, I'm going to zoom in by a factor of 60. Just going to type that in. I'm going to grab my rules. Reasonably accurate top dead center. Reasonably accurate top dead center, 720 degrees later. I have my 4 divisions. I have my 4 strokes. I want to measure the EVO. So I grab my cursor. I want to get it on top of that 180 as best I can, but with Pico, I can be a little bit lazy. I'll just type in 180 and I'll move the cursor for me. So I got a rock solid 180. I get my other cursor. And I'm going to use the same method. I'm going to zoom in and I'm going to go to times 20, same as I did before. So it'll be kind of an apples to apples. I'll bring the 0 up. I don't want to bring it up too far because I got something else to look at. I'll turn on a filter with the same control, 6 kilohertz, just to clean up the pattern. And I will tweak this just a little bit, but I think that's pretty darn good. I think that's when the pressure changed direction, and it's 42 degrees. Now, 42 is within the window of 60 to 30. However, what was the other one? You recall? Of course you do. So it was about 57, 58 degrees, so it's almost 60. So there's almost a 20-degree difference. Let me do one other thing. I measured the duration. My rough math duration on the good one was about 230. So I'm going to grab my other rule. Now this one's much easier. I have a much higher level of confidence in telling you where the exhaust valve closed than I did previously. The reason for that is that point right here you see a significant increase in pressure. I believe that's when the exhaust valve closed. That piston was coming up, the valve closed too soon, and we compressed air in that cylinder. So I could be off a little bit, but I'm not off that much. So my duration is 176 degrees. So before it was reasonably 230. So I have less duration, and I have an EVO that's shifted about 20 degrees. You know what's wrong. I know you know what's wrong. Let me show you what's wrong. Once again, I'll give everybody a moment. Take a look.
We can see it, John.
Thank you, Kurt. So you can see that the lobe is worn out. And of course, the roller lifter is shot as well, but the cam lobe is completely worn. This is why I am such a fan of this method. In-cylinder analysis gives us the ability to determine what's wrong with a high degree of accuracy prior to disassembly. Now, once upon a time, we would take it to this level and to say, okay, yeah, this is what it was. But we have a pretty high level of confidence today with this. So I hope that example gave you a pretty good idea of how to use some of the methods and the techniques. So let's get back to the presentation. So the next one I want to talk about is an intake path restriction. And these are not as common, but these can be tricky, which is why I've kind of included it. So normally, if you think about a running engine at idle, the restriction to airflow is supposed to be the throttle blade. That's what creates the 18, 19, 20 inches of vacuum in the intake manifold. That's the normal restriction to flow. So when I talk about an intake path restriction, I'm talking about something else that's restricting airflow. Now, it could be before the throttle blade, like a completely plugged air filter or rags, but I'm going to stay focused between the throttle blade and the intake valve. So you could have an intake valve that's not opening far enough. You could have an intake valve that's got, or the port, the tract is heavy carbon deposits. Somebody did engine work, they forgot to pull a rag out. That would be an intake path restriction. And on some variable valve lift systems, most notably the BMW Valvetronic and maybe the Nissan VVL, by design, the restriction to airflow is the intake valve. It's not the throttle blade. Not in all cases, but in many cases. So if an engine's got variable valve lift, and we would know that, of course, we would know what we're working on, you'd have to consider that. So there are some really good clues for intake path restrictions. The clue that's the most common clue is that we open the throttle blade as much as we can, and we try to force as much air into the engine, and we look at the pressure. So I like doing brake torques in reverse, when I can, or a wide open throttle snap in park or neutral. So, and that method has been used for many years with compression gauges and Schrader valves removed. There's another clue that you can see with an in-cylinder pressure transducer at idle, and that is how deep that intake stroke is. You've heard me say from the beginning of this session that probably the deepest vacuum that a gasoline engine is capable of is maybe 26 to 28 inches. More commonly 20, 21, 22. There are some that bump into 23, 24. That's not typical. Examples of an intake path restriction, I know you heard me say a couple, but the worst case scenario is the valve doesn't open. Heavy deposits is a possibility, not light deposits, heavy deposits. And unlike an exhaust path restriction, a retarded cam. So on an exhaust path restriction, advanced cam could cause a problem. Here is retarded cam, because when a cam is retarded, everything occurs later. The valve opens later, and of course it closes later. And it's the opening later that causes the restriction to airflow, because the piston is moving down, but if the valve hasn't opened, we're not pulling air in the cylinder. And that's true with a worn lobe as well. So that's what a worn lobe and a retarded intake cam have in common. They, in both cases, the valves open later. I am looking at the clock, and I think I can get 2 more examples done. So my first example is pretty straightforward. It's a worst case scenario, but it's a good way to start. So I have a Corvette engine that's been highly modified, excuse me. It's got high performance cylinders head. It's hard to tell in a picture. It has nitrous oxide on it. It's got a tune in it. So it's a 2000 Vet with a 5.7 that runs poorly. That is the complaint. And again, it has nitrous. It's high performance. And the tech, when I first talked to them on the phone, tells me a little bit about it, and I confirm this when I get there, and you'll see in blue here, there's the great clue: this engine burns oil. This engine burns so much oil that when it runs, I see blue smoke out the tailpipe, which is something you don't see on modern day engines much anymore. So this thing burns some oil. So keep that in the back of your mind as we progress. So the very first test that I do, I can't use a scan tool because of the tune in the PCM, but the very first test that I do is a cranking current test. So blue is the #1 ignition coil trigger, so I back probe the trigger signal for #1 as reference, and red is a high amp current probe clamped around a battery cable. Phenomenal test, phenomenal test. And I disable ignition, I crank the engine over. And I can hear, as you can see, I have a cylinder with low compression. So if I open that up, that's #1, that's #1 again. And these, I should have 8 compression pulses. And clearly, there's 1 missing. So I use my Pico overlay. I know the firing order, and I quickly determine, as you could determine yourself, that cylinder #2 is my problem. It has very low compression. So this is how I know #2 is my guy. So I go in cylinder #2 and I perform a cranking compression test. And it's absolutely horrible. It's absolutely horrible. And the tech now thinks that I'm helping. Wow, this is a worst case scenario. You know, they're going to have to pull the engine. It's just horrible. So I'm going to open this up a little bit, zoom in on one of the events, and so there's my 0. So my peak compression is a whopping 16 PSI. So this is why the engine runs poorly. 16 PSI, of course, is horrible. So the question becomes, and I expect you to answer this before I get there, the question becomes, do I have a big hole in the cylinder? Is there a chunk of that exhaust valve that's fallen off? Is there a hole in the piston? Did the nitrous burn a hole? Did they break some rings or damage the wall? I mean, what did they do here to make this compression so horrible? Let's see if we can get a handle on it. So we're going to use a little common sense as we walk our way through this. So there's my 0. I have what I would consider to be a symmetrical compression tower. Pressure we start with is the pressure that we end with. So I'm starting to build pressure. You can see my horizontal line down here. I'm building pressure. I hit a peak. Yes, it's low, but I hit a peak, and I come down on the expansion stroke, and I see an abrupt change. And we all know that's EVO. So I know the exhaust valve opened. So one could argue, if that's the exhaust valve opening, the exhaust valve was probably closed prior. So the exhaust valve was closed, and now it opens. And I believe it opens pretty well because we lose pressure and we come up to 0. And of course, an exhaust stroke, and this has no phasing, is normally 0 PSI, and this is right there. So I am kind of determining that because I had an EVO, my exhaust valve was probably closed and it probably opened. And now I move to intake. And I see something that's weird. Now this engine is cranking, it's not running. I have very little vacuum in the intake manifold, but I have a huge amount of vacuum in the cylinder. So it's about 26 inches of mercury. And again, you've heard me say 26 to 28 is probably the lowest you'll ever see on a gas engine. So I have really, really low vacuum. Do you think I could pull that kind of vacuum with a hole in the piston or a chunk of the exhaust valve? This cylinder doesn't have a leak. I have a symmetrical compression tower. Yeah, it's really low compression. And I have EVO, I have an exhaust valve event. I don't think I have an intake event. This is very, very rounded. There's a lot of time spent in a vacuum. You've heard that term before. So if I look at some analysis, I got super low compression. I got a very deep intake stroke, vacuum or pull, and I don't really see a clearly defined change here. And I know you know what's wrong. The intake valve's not opening. So we did some preliminary investigative surgery, if you will, pull the cover. And obviously you can see by looking at the high performance rocker, the tip of it is broken. Now the push rod was there, I removed the push rod. So, and fortunately, we found the parts. So that worked out pretty well. You can see how clean the engine is. So I'm guessing under a high boost condition, it busted it. But I don't really care about that. The bottom line is that we have an intake valve that's not opening. And let me just kind of wrap something up here. You know, theoretically, if valves don't open, you can't get air in or out of the cylinder. So if an intake valve doesn't open, you have to ask yourself, as bad as 16 PSI is, air came in and air comes past the rings, just like it did at the very beginning of our conversation with that 5.3 GM AFM engine. It gets past the rings. However, if an exhaust valve is functioning, but the intake valve isn't functioning, every time that piston goes down and reaches that, that deep vacuum, it's going to start to evacuate the crankcase. So not only is it going to pull air out of the crankcase, it's going to pull oil out of the crankcase. And that's the reason for the oil burning. So hopefully connecting all the dots makes this work. So Kurt, I had one more example in our remaining 8 minutes, but I know that we have questions. So are there some questions that I should address?
Honestly, there's not a lot of questions. I'd say let's squeeze the last one in.
I'll squeeze the last one in. I think you'll find it kind of interesting. So I have a 2011 Cherokee with a 5.7 Hemi. The engine has a single cylinder misfire. The most critical information is that this engine barely misses at idle. And if it wasn't for the check engine lamp, there probably would be no concern. So there is a miss, and that miss can be felt, and that miss can be seen at higher RPMs. So when I connect the scan tool, I have a mill, I have a P0305, so cylinder 5 is the misfire, but I only see counters activity at an elevated RPM. The higher the RPM, the worse it is. The lower the RPM, matter of fact, it rarely misses at all. Runs like a Hemi runs. So I do some analysis with the scan tool, and I decide I'm going to go in cylinder. And I do 2 cylinders, a good cylinder and a bad cylinder. Cylinder number 5 and a good cylinder. And when I go into cylinder number 5, I do a wide open throttle crank to maximize the amount of airflow into the engine. And it looks pretty good. My cranking compression is about 223 PSI, which is pretty healthy so this is the bad cylinder, it's pretty healthy. And then I fire it up and I let it run. And I'm studying the running compression pattern. You will make me very happy, audience, if you can see what's wrong. So let me assist your eyes. Again, we're talking about an intake path restriction, so you know where to focus your eyes. I'm going to open this up. It's subtle, but it's there. Divide this up. I'm going to zoom in a little bit. Look at the depth of the expansion stroke vacuum and the intake. Please notice they start out good. That depth, about 22 inches, then something happens. Something happens that pulls it even deeper. So we started out okay, then something happened, and we pulled even deeper before we go back and start to move upward on our compression stroke. So that's about 22 inches, and that's pulling about 24 inches. So it's not as bad as that Corvette example a moment ago, but something is there. Something subtle is going on there. Here's a good cylinder for comparison. And you can kind of tell right away that as I zoom in, there's a difference in depth, which again, Hemis have pretty aggressive cam timing, but sorry about that. But it's horizontal across. So what I don't like is this. So I think there's something going on. So here's how I would prove this. So cylinder number 5 is the bad cylinder. Transmission's in park. I'm doing as aggressive as I can. Accelerator pedal snaps. And I am bumping into, let's say 225 PSI, at least 200 easy, not getting to 250. This is cylinder number 1, my known good cylinder. The scales are going to stay the same. I'm not changing any scales. Well over 300 PSI. So 300 PSI snap on a good one, under 250 on a bad one. I do a brake torque in reverse. So this is the bad cylinder. So I'm doing an aggressive brake torque in reverse. The throttle blade opens on this engine. And I have about, you can see 200, I'm about 180 PSI as I level it off. Horrible, by the way. I go to the good cylinder. I'm at about 317, 15 PSI. This is a classic example of an intake path restriction. This cylinder cannot get enough air in. Now, if it's a single cylinder misfire, it's something specific to the cylinder. So it's specific to the cylinder. And I can do more analysis. You know, the clock's ticking and I don't want to extend my time, but the most likely condition is a worn lobe. Now, these photographs are not from this engine. I never got photographs from that particular engine. This is from another Hemi that I was involved with, but you can see the wear and tear. And I've seen a number of these Hemi engines without trying to be a pattern failure technician that have worn intake lobes. And they're sometimes difficult to diagnose because they don't really show up at idle. You have to force more air into the engine. But I guess I'm going to kind of summarize by saying that if a tech knows what to look for, you can see the subtle clue where the intake valve closed way early and we pulled deeper in the vacuum. So that depth is not because of the throttle blade, it's because of the restriction into the intake. In my remaining minutes, I'm going to jump towards the end of my presentation. I skipped, I had one more case study on cam timing, but that's okay, another day. So I'm going to wrap up. My goals for this class were to explain why this may be the best way for a student or tech to truly understand the 4-stroke cycle and 4 valve events. I truly believe this is the case. If a tech looks at in-cylinder, performs in-cylinder, their mechanical education will improve dramatically. Hopefully the methods that I use, my explanation could be beneficial to you as you share information with your students and the examples as well. So I want to thank everyone for allowing me to participate and listen to me for the past 90 minutes. Thank you very, very much, and have a great rest of the day in your virtual conference. Thanks, Kurt.
John, thank you very much. As always, packed full of great information. We really appreciate you. We really appreciate everybody being here this morning. We look forward to you in a session later this afternoon. And as a reminder to all of our members, we have our virtual annual member meeting tomorrow. So again, thanks again, John, and everybody have a great rest of the day.
And you're shutting me off, right, Kurt?
I'm going to shut you down.
Great.
Thanks
okay.
so much, John.
You're welcome. Thank you. Thank you.